Hey all you electric junkies out there, in today's video we will be diving into a Gibson Ga4 reverb echo unit from the 1960s. It is a vacuum tube based effect designed around the famous Tel-Ray Adineko memory system, more commonly referred to as an oil can delay, that was invented in the 1950s by Ray Lubbow. The current state of the device is rather unknown. The previous owner didn't know much about it other than it quit working years ago. Given its obscure history, this leaves us with quite the mystery to uncover. As I begin with the disassembly, let's go over the control panel and the components external to the chassis. Starting on the left, we have two instrument inputs for high impedance devices like an electric guitar. A high-level input you can use to send a signal from a mixing board console, a loudness control which dampens the signal sent into the high-level input. The direct control adjusts the unaffected or dry signal level sent to the output. The reverberation control, which adjusts the intensity of the delayed signal. Three-way mode switch, which allows you to select between mode 1, a short delay, mode 2, a longer delay, and mode 3, a combination of the two, giving a reverb effect. The output jack, pilot light, power switch, and 1 amp fuse holder. The foot switch is hardwired. We have our tubes, 3 RCA connectors going from the oil can to the chassis, the power transformer, and an AC power plug connecting the motor to the chassis. For the initial test, let's take off the drive belt and power it up through the current limiter, see if it passes signal. Using a Telecaster as the signal generator, plugged into the instrument jack, sending the output to a practice amp under the bench. Nothing. Let's turn up the direct control. Beautiful, it passes signal. Let's briefly go over the electromechanical portion of this device, how it functions, and what we expect to see inside the can. This is a block diagram lifted from the patent Ray Lubbow filed for February 21st, 1958 for his delay apparatus. The signal flows from the source to the writing electrode. The electrode is comprised of a graphite impregnated neoprene wiper. As the insulator moves past the electrode, the AC voltage builds up and induces an electrical field on the surface of the disc, forming a replica of the voltage where each tiny area of the insulating surface is acting like a mini capacitor, capturing the value of the voltage as the electrode brushes past the disc. In a dry environment, the charge would dissipate into the air pretty quickly. As the disc rotates, it picks up the LB65 oil in the bottom of the can, coating the surface and providing an insulating layer over the disc, trapping the charge and preventing its dissipation into the air. The stored charge is then read by the pickup electrode, which is identical to the writing electrode, and positioned a distance therefrom to provide a desired delay interval. The signal is then sent out to an audio reproducing device for amplification. So in summary, the effect is created when our signal is split in two. One way bypasses the oil can, giving us our dry signal, which is then amplified. And simultaneously, our signal is sent into the can for a quick trip around the disc, and it is then amplified and mixed with our dry signal at the output. Here's the oil can out on the bench. Let's go ahead and take off that front lid. There isn't much oil in here. The little bit I see at the bottom looks thick and dirty. The disc looks to be in great shape, no scratches. Let's remove the old oil. I've removed as much of the oil as I could, but we've run into an issue. Looking towards what would be the bottom of the can, you see that amber color? Looks like over the years some of the oil has crystallized. And because the disc mechanism is off center and I can't reach it, we're going to have to remove the rest of the can. I'm going to try using some solvents to dissolve it. No luck with the solvents, so I resorted to using a cutoff wheel on my Dremel tool. I used it to scribe a line down the middle, just enough to break it into 2 pieces. You can see how it conformed to the shape of the lip. Taking a closer look at the electrodes, we can see that the disc makes contact with the electrode towards the edge, but as we look towards the center, there's a gap. The wipers are currently at a 30-degree angle off the center line of the disc. Let's rotate them over so they are parallel with the center line by adjusting these 2 nuts that affix the electrodes to the top panel for better contact and optimal transfer of the signal. Check out the pearlescent finish on the disc. That is the dielectric metal oxide layer. The internal components have all been thoroughly cleaned with alcohol. Then I applied a light coat of the LB65 oil. The can has been reattached using C-clamps. We're going to add 2 tablespoons of the LB65 lubricant into the can. I've powered on the motor. As you can see, the disc is spinning inside. And we have good contact of the wiper to the disc. And if you look at the edge closely of the disc, when I shut off the motor, you can see the oil start to get pulled down by gravity. So while it's not much, those 2 tablespoons of the oil are just enough for the disc to dip down the bottom to replenish itself. After gently tapping the front lid in place, we're going to tip it on its side so we can let it rest for 10 minutes and check for leaks. Prior to the cleaning of the can, I removed this armature in order to replace the old stretched out drive belt. We have some replacements here that I purchased on eBay. After lifting up the oil can, I was pleased to find no signs of leaks on the paper towel. The new drive belt has been installed. Also went ahead and cleaned and lubricated all the moving parts to the motor. Put this little piece of blue tape here so we can see how fast the drive wheel spins. Let's go ahead and test it out. Got the motor hooked up to the variac. We're going to slowly bring it up. Got our first signs of life. Stop at 120. There we are. It's nice and quiet, very smooth operation. Last thing before returning the oil can to the chassis, we're going to carefully unscrew this bolt so we can replace the remnants of what used to be a strain relief clip for the RCA cables. There we go. The strain shall be relieved. Let's go ahead and put the can back into the cabinet so we can move on to the electrical circuit. Here we have the schematic. Let's go ahead and trace our signal starting at the inputs. They are all summed up here to this point, where the signal is then split between the wet and dry portions of our circuit. On the dry side, our signal is injected into the grid of this triode for amplification. Leaving the plate, we pass through this voltage divider, dropping about 2/3 of our signal to ground. We come into a buffer. We leave the cathode. And here we have the direct control, where we can attenuate our signal. On the wiper, we have the mixing resistor to the output. On the wet side, we have our signal coming down here into the grid of this triode stage for amplification. Leaving the plate, we pass through a voltage divider, dropping our signal, as well as a low pass filter, cutting out some lower frequencies. And this capacitor here is bypassing some treble frequencies straight to the grid of this amplification stage. Coming off the plate, our signal is then fed into the 3-way mode switch, where at the input we have these 2 Zener diodes that are providing protection from voltage spikes. Here's the oil can. We have 3 connections. Looks like connections 1 and 3 will be the writing electrodes, and number 2 would be the read or pickup electrode. So depending on our selection with the switch, our signal is either sent through the short or long path or both, and then it is picked up at connection 2, where our signal is then sent into the grid of this amplification stage. Leaving from the plate, we come to another buffer. Signal leaves through the cathode, feeding our reverberation control. On the wiper here, we also have the foot switch, so we can ground out our signal. And the other mixing resistor, where our signals are then summed at the output. Down below, we have the power supply. On the primary side, we have our power switch on the hot, fuse on the neutral, death capacitor going from the hot to ground, our pilot light, and AC plug for the motor. On the secondary, we have our 6.3 heater winding, with one side of the winding being grounded, the high tension winding, along with the rectification circuit, which is comprised of these two diodes in series, and these two capacitors in series, bridged with the winding. This is known as a D-Lon voltage doubler. We have a dropping resistor going to node A, which feeds our two buffer stages, a 40 microfarad cap to ground, another dropping resistor to node B, which feeds the rest of our circuit, along with another 40 microfarad cap. Got the chassis out on the bench. Starting on this side, we have that 2-prong AC outlet for the motor, along with where the power cable exits the chassis. We have a rather stout power transformer, considering it's just a 3 preamp tube circuit. Looks like it says on the sticker 606, making it a Schumacher transformer. Our foot switch comes into the chassis here, along with our RCA jacks to the oil can, which have been color coded, matching the plugs. Let's take these tube shields off. Looks like somebody's marked that socket for a 12AU7. And we have a vintage RCA 12AU7. RCA 6EU7. And another RCA 6EU7. Taking our first look inside of the chassis at the electrical circuit, it's pretty easy to tell that some work has been done in the past. The death cap is still in circuit. The original 2-prong power cord has been replaced with a modern 3-prong grounded cord, along with a non-original power transformer. You can see the original holes with a smaller footprint. We have replaced electrolytic capacitors in the power supply. The audio portion looks mostly original, aside from the cathode bypass capacitors that have been replaced. The casings from some of the caps have been burned from a clumsy soldering iron. A date code on the back of one of the pots reads 1346511, making it a Centralab pot made the 11th week of 1965. Looks like the input resistors have been replaced along with the jacks. I looked up the new power transformer, and it appears to be a replacement for a Fender Princeton Reverb reissue. It's not the ideal replacement for this circuit. It's designed for a circuit with a much higher current draw, and obviously is physically much larger than the original. A better match electronically would have been a replacement transformer for a Fender 6G15 reverb unit that are readily available and would have probably fit in the original space without having to alter the chassis. With our new transformer outputting much more voltage than the original, the voltage doubling circuit was no longer appropriate and a full wave rectifier is in its place. At the first node, we have two 20 microfarad caps in parallel for a total of 40 and rated for 500 volts. A 22,000 ohm resistor instead of the original 25. We have a 20 microfarad cap at node A, Looks like two 20 microfarad caps in parallel at node B, along with another 22,000 ohm dropping resistor, which appears to be wired in parallel with the original 10K resistor that's been left in circuit. Since there has been some extensive work done in the power supply in the past, we are going to take some voltage readings and see how they compare to those published on the schematic. When dealing with high voltage power supplies like this, it's best practice to drain the stored DC voltage in the filter caps after powering down the device before proceeding with any work in the chassis. With 120 volts coming through the variac, starting with the power rail, on the first node we have 490 volts DC. Swapping over to the white clip, we have 287 volts on node A. And now on node B, with the yellow clip, 268 volts. I've recorded them on this chart along with the voltages from the schematic, and I will repeat the same process throughout the rest of the circuit on the plates of the amplification stages and cathodes of the buffers. Comparing the two, our voltages are a little bit lower, but the general trend is there. So the tubes check out, and the replacement power transformer is more than enough for our circuit. The capacitors at the first node are only rated for 500 volts. We are seeing 490 on the first node, and when we factor in the inrush of power at startup, we are going to need more than a 500 volt rated cap. Originally, we saw two capacitors in series in this position, allowing for a higher voltage rating. Besides that, the circuit is in great shape. For purely aesthetical reasons, we will replace those burnt bypass capacitors, as well as the input resistors with period correct carbon comps. Using Ohm's law, we should be able to calculate a smaller resistance value for that first position dropping resistor, bumping up the voltage closer to what's on the schematic. Starting with our voltage on the first node of 490, we subtract our desired voltage, giving us a voltage drop of 150 volts. Now to find our resistance value, we know we need to divide voltage by the current passing through. At the first node, we have 620 volts, and we subtract 340, giving us a 280 volt drop. Divide that by the resistance, 25,000 ohms, and we get our current 0.0112 amps. Now that we have the current, we can divide 150 volts, and we get 13,392 ohms. We can round that to 13K. I've removed the replaced components in the death cap, and the chassis has been thoroughly scrubbed. In their place, we're going to install a 47 microfarad capacitor for node B, another 47 microfarad cap for node A, and at the first node, we're going to wire two 47 microfarad caps in series, bumping the voltage rating way beyond our actual voltage present, along with two 470K balance resistors. A 5 watt 13K resistor for the first position, and in the second position, we have a 2 watt 220K resistor in parallel with the original 10K resistor that I tested while it was isolated from the circuit. It checked out at 10.5K, so our parallel resistor won't reduce the resistance by much, but it will relieve the stress on our little half watt component. Swapping out the carbon film for carbon comp resistors, the bypass capacitors have been replaced, giving it a much more uniform look to the repairs. Now that our new power supply has been installed, let's perform another voltage check on the entire circuit. Before this, I formed the new capacitors by gradually stepping up the voltage 10 volts at a time every 15 to 20 minutes. Here are the new readings, and it looks like the 13K resistor bumped our voltages right up to where they are in the schematic. Now that all the work has been done, let's go ahead and do a little sound demo. Got my guitar plugged in, direct knob at about 5 o'clock, giving us this dry signal. And let's bring up the reverberation knob. All the way at 10, we do get some noise, so let's bring it back to about 7. And we're in mode 1, the shortest delay. Mode 2. Mode 3. Let's bring it back to mode 1, jam a bit. Mode 2. And mode 3.